You thought you understood scale. You thought the first part of our journey, the discovery of quasars, the mechanism, the physics, had prepared you for what comes next. It hasn't. Because now we're going to talk about the extremes, the record holders, the quasars that exist at the absolute boundaries of what the universe allows. Objects so distant they're showing us epochs when the cosmos was fundamentally different. Objects so luminous they make everything we've discussed seem dim by comparison. Black holes so massive they shouldn't exist. Growth rates that violate what we thought were physical limits. Welcome back to Echoes of Deep Time. This is the second part of our exploration of quasars, and I need you to understand something from the start. What we're about to discuss isn't just impressive in scale, it's genuinely unsettling. These objects challenge our models. They exist in configurations that force us to reconsider our assumptions about how the universe works. The records aren't just numbers to admire, they're puzzles, anomalies, objects that shouldn't be there according to our best theories, and yet there they are, shining across cosmic distances, daring us to explain them. Let's begin with distance, with the most remote quasars ever detected, with light that has been travelling toward us since the universe was barely recognisable as the cosmos we inhabit today. The current record, and this may have changed by the time you hear this, because JWST is finding new distant quasars regularly, is a quasar designated JWST Z140. Though the exact record holder shifts as new observations are confirmed, what matters isn't the specific name. What matters is what these objects represent. We're finding quasars at redshifts above 10. Some candidates push toward redshift 14 or 15. Let me translate what that means. Redshift measures how much the universe has expanded since light was emitted. A redshift of 10 means the universe has expanded by a factor of 11 since those photons began their journey. The wavelength of light has been stretched by that same factor. Ultraviolet light emitted by the quasar arrives at our telescopes as infrared radiation, shifted across the entire visible spectrum and beyond. But more importantly, redshift tells us when. A quasar at redshift 10 existed when the universe was roughly 480 million years old. For context, the universe is now 13.8 billion years old. We're seeing these objects at roughly 3% of the universe's current age. The universe at that epoch was unrecognisable. Galaxies were just forming. The first generation of stars, the population of the 3 stars, born from pure hydrogen and helium with no heavy elements, had only recently lived and died. The intergalactic medium was still mostly neutral hydrogen, opaque to ultraviolet light. The cosmic dark ages were ending, and the epoch of reionization was beginning. And in this infant universe, barely 500 million years after the Big Bang, we're finding supermassive black holes with masses of hundreds of millions to billions of solar masses, actively accreting, shining as quasars, existing in an epoch when there supposedly hasn't been enough time for them to form and grow to those masses. This is the problem of early quasars, and it's profound. Remember the growth timescale I mentioned in the first part? A black hole accreting at the Eddington limit, the maximum sustainable rate, has an E-folding time of about 45 million years. If you start with a 100 solar mass seed black hole and let it grow exponentially at this rate, you can reach 1 billion solar masses in roughly 1 billion years. But these quasars at redshift 10 or higher didn't have 1 billion years. They had less than half that. And they still managed to grow black holes to masses of hundreds of millions or billions of solar masses. The math doesn't work, not with standard assumptions. So either the seed black holes were much more massive than 100 solar masses, which raises the question of how those massive seeds formed, or the black holes were accreting faster than the Eddington limit, which we thought was a hard constraint, or the universe found some other mechanism we haven't thought of. This isn't a small discrepancy. This is the universe telling us we're missing something fundamental about black hole formation or growth in the early cosmos. Let me tell you about one specific object, a quasar called UHZ1. It's not the most distant, but it's remarkable for other reasons. This quasar exists at redshift 10.1, about 13.2 billion light-years away in light travel distance. It was discovered by the Chandra X-ray Observatory and confirmed by JWST. The black hole powering UHZ1 has an estimated mass of roughly 40 million solar masses. That's relatively modest by quasar standards. We know of black holes hundreds of times more massive. But UHZ1 existed just 450 million years after the Big Bang. For this black hole to reach 40 million solar masses in that time, it would need to have been accreting at or near the Eddington limit almost continuously since the earliest possible epoch when black holes could form. There's almost no margin for error, no time for dormant periods, no room for inefficient feeding, and UHZ1 isn't alone. We've found dozens of quasars at similar or even earlier epochs. Each one presents the same puzzle. Each one requires growth rates that push against theoretical limits. Some astronomers have proposed that these black holes are accreting in super Eddington modes, that under certain conditions, perhaps in very dense gas-rich environments with specific magnetic field configurations, matter can fall onto the black hole faster than radiation pressure should allow. The radiation escapes preferentially in certain directions, perhaps funneled by the magnetic field, allowing matter to continue falling in from other directions. This might work. Simulations show it's possible in principle, but it requires fine-tuned conditions that may not be common, and it's not clear the early universe could maintain those conditions long enough to grow billion solar mass black holes. Others suggest the seed black holes were much more massive. Instead of forming from the collapse of a single massive star, producing a seed of perhaps 100 solar masses, maybe the first black holes formed from the direct collapse of massive primordial gas clouds. These clouds, if they collapsed without fragmenting into stars first, could create black holes with thousands or even hundreds of thousands of solar masses from the start. 100,000 solar mass seed gives you much more time to reach billion solar mass scales. The growth problem becomes manageable, but direct collapse requires very specific conditions. The gas cloud needs to be massive enough, dense enough, and hot enough to collapse directly without cooling and fragmenting. It probably needs to be metal-free, no heavy elements to provide efficient cooling, and it needs to avoid forming stars which would disrupt the collapse. These conditions might have existed in the very early universe, in regions where the first galaxies were assembling, but we don't know how common they were. We don't know if they can explain the abundance of early quasars we observe. There's also a more exotic possibility: primordial black holes. Black holes that formed in the first fraction of a second after the Big Bang, from quantum fluctuations in the dense early universe. These could have any mass, including masses large enough to seed supermassive black holes. But primordial black holes are speculative. We have no confirmed detections of them. They're an idea, not an established phenomenon. Using them to explain early quasars feels like explaining one mystery with another. The truth is, we don't know. The early quasars are presenting us with a genuine puzzle, and the solution isn't yet clear. Multiple research groups are working on this problem, running simulations, developing new formation scenarios, searching for more early quasars to better characterize the population, and JWST is finding them. Nearly every deep field observation JWST conducts turns up candidate high redshift quasars, objects that appear as faint red points in the images, their light stretched into the infrared by extreme redshifts. Each one needs spectroscopic follow-up to confirm the redshift and characterize the black hole, but the sheer number of candidates suggests that massive black holes in the early universe might be more common than we thought, which makes the problem worse. If these objects are common, then whatever mechanism creates them must be robust, not rare. The universe must have a reliable way to form and grow supermassive black holes quickly. And we need to figure out what that way is. Let me shift to another record: luminosity, the brightest quasars ever observed. The current record holder for intrinsic luminosity, the actual energy output, not just apparent brightness, is a quasar called J05294351. This object, discovered relatively recently by analysing data from wide-field surveys and confirmed with spectroscopy, has a luminosity of approximately 5 times 10 to the 41 watts. Let me put that in perspective. The Sun's luminosity is about 4 times 10 to the 26 watts. This quasar is roughly a quadrillion times more luminous than our Sun. If you placed it at the distance of the nearest star system, Alpha Centauri, it would appear brighter in our sky than the Sun. From 4 light-years away, it would be blinding. J05294351 is accreting matter at an estimated rate of roughly 1 solar mass per day. Per day. Every 24 hours, the equivalent of an entire star's worth of matter is spiralling into this black hole, being heated to millions of degrees and radiating away its energy across the electromagnetic spectrum. The black hole, powering J05294351, has an estimated mass of 17 billion solar masses. That's among the most massive black holes ever discovered. For comparison, the black hole at the centre of our Milky Way is only 4 million solar masses. The black hole in M87, the one imaged by the Event Horizon Telescope, is about 6.5 billion solar masses. 17 billion solar masses is approaching the theoretical maximum for black hole mass, the point at which feedback becomes so powerful that further growth is effectively impossible. This black hole is near the ceiling of what the universe permits, and it's not alone at these extreme luminosities. There are other quasars in the same luminosity range. TON 618, another ultra-luminous quasar, has an estimated black hole mass of around 66 billion solar masses, though this estimate is uncertain and debated. If correct, it would be the most massive black hole ever found, and its luminosity, while lower than JWST 4351's current output, has likely been comparably extreme during peak accretion episodes. These ultra-luminous quasars are rare. We've only found a handful across the entire observable universe, but their rarity makes sense. To achieve these luminosities requires both an exceptionally massive black hole and an exceptional fuel supply. You need billions of solar masses of gas available to accrete, and you need it delivered at rates approaching or exceeding 1 solar mass per day. Those conditions don't persist for long. The quasar's own radiation will blow away the surrounding gas relatively quickly. The ultra-luminous phase might last only a few million years before the fuel is exhausted or expelled. We're catching these objects in a brief, spectacular moment of their existence. The radiation from these quasars affects their surroundings on galactic and even intergalactic scales. Within the host galaxy, the intense radiation field ionizes all the gas out to distances of hundreds of thousands of light-years. Star formation is suppressed or shut down entirely across the galaxy. Molecular clouds are photodissociated. Atoms are stripped of their electrons. The quasar drives winds, massive outflows carrying energy and momentum into the surrounding space. These winds can reach velocities of thousands of kilometers per second, fast enough to escape the galaxy entirely. They carry metal-enriched gas, elements heavier than hydrogen and helium, produced by previous generations of stars, into the intergalactic medium, polluting the pristine primordial gas with heavy elements. On larger scales, the quasar's radiation creates a cosmological Strömgren sphere, a bubble of ionized gas expanding through the intergalactic medium. The size of this bubble depends on the quasar's luminosity and the density of the surrounding gas. For the most luminous quasars, the ionized bubble can reach hundreds of millions of light-years in diameter. These bubbles are important for understanding the epoch of reionization, which we'll discuss in detail shortly. For now, just understand that the most luminous quasars are not passive beacons. They're transformative forces, reshaping the structure and state of matter across cosmological volumes. Now, let's talk about speed. Not the speed of jets, we've covered that, but the speed of black hole growth. There's a quasar called SDSS JO100+2802 that holds records in multiple categories. It exists at redshift 6.3, meaning we're seeing it as it was about 900 million years after the Big Bang. The black hole powering this quasar has an estimated mass of 12 billion solar masses. 12 billion solar masses in 900 million years. For this black hole to reach that mass in the available time, it would need to have been growing at or above the Eddington limit continuously. There's essentially no time for dormant periods. The black hole has been feeding voraciously since the earliest possible epoch, and we can calculate how much mass it's accreting right now based on its observed luminosity. The answer is roughly 50 solar masses per year. That's the mass of 50 stars being consumed annually. Every week, this black hole is accreting roughly the mass of our Sun. This isn't sustainable indefinitely. At this rate, the black hole would exhaust any realistic fuel supply in a few tens of millions of years. The quasar is in a temporary phase of extreme accretion, powered by some recent event, perhaps a galaxy merger, that delivered a massive amount of gas to the central region. But even temporary, it's extraordinary. 50 solar masses per year translates to about 0.14 solar masses per day. That's about 200 times the mass of Earth accreting every 24 hours. The energy release from this accretion is staggering. Another rapid growth object is a quasar designated JWST 3422 (928), observed at redshift 7.54. This quasar existed only 690 million years after the Big Bang, and it hosts a black hole of roughly 800 million solar masses. Again, the growth timescale is a problem. To reach 800 million solar masses in 690 million years requires near-continuous Eddington-limited accretion, and this black hole is still growing fast. Its current accretion rate, based on luminosity, suggests it's adding tens of solar masses per year. These rapidly growing black holes are important because they represent the upper end of the growth rate distribution. Most black holes probably grow more slowly, with longer dormant periods between feeding episodes. But these rapid growers show us what's possible under optimal conditions. They also constrain our models. Any theory of black hole formation and growth has to be able to produce objects like SDSS J100 plus 2 802 and J144 Nantuscate. The theory has to permit rapid growth to multi-billion solar mass scales within the first billion years of cosmic history. Not all theories can do this. Some formation scenarios are ruled out by these observations. The existence of these objects is falsifying hypotheses and narrowing the range of viable models. Let me tell you about jets, because some quasars have the most powerful jets ever observed. The radio galaxy Hercules A, technically not classified as a quasar because we're viewing it from the side rather than down the jet, but powered by the same mechanism, has jets that span roughly 1.5 million light-years. The total energy in these jets, summed over their history, is estimated at around 10 to the 61 ergs. That's the energy equivalent of converting roughly 10 million solar masses entirely into radiation at 100% efficiency. Of course, the conversion isn't 100% efficient, it's around 10% for accretion, so the black hole actually consumed something like 100 million solar masses to power these jets over their lifetime. The jets terminate in lobes, vast bubbles of energized plasma that are actively displacing the surrounding intergalactic medium. The energy injected by the jets is heating this medium, preventing it from cooling and forming new galaxies. On cluster scales, this feedback is thought to regulate the population of massive galaxies, preventing them from growing too large. Another spectacular example is the Blazar 3C 450-3, one of the most violently variable objects in the gamma-ray sky. Because we're looking nearly straight down the jet, relativistic beaming amplifies the emission enormously. The apparent luminosity, boosted by the jet's orientation and velocity, can exceed 10 to the 42 watts during flares. These flares occur on timescales of hours to days. The brightness can double or halve in less than a day. This tells us the emission region is extraordinarily compact, light hours across, and the particles are being accelerated to extreme energies by processes we still don't fully understand. The gamma rays from blazars like 3C 454.3 have energies exceeding 10 billion electron volts. These photons carry thousands of times more energy than visible light photons. They're produced by relativistic electrons, particles moving at 99% of light speed, scattering lower energy photons and boosting them to gamma ray energies through inverse Compton processes. When these gamma rays travel across cosmological distances, they interact with the diffuse background light filling the universe, starlight and dust emission from all the galaxies between the blazar and us. The gamma rays and background photons can annihilate, producing electron-positron pairs. This process attenuates the gamma rays, especially at the highest energies. By measuring how much attenuation occurs, we can actually map the density of background light along the line of sight. The blazars become probes of the intergalactic radiation field. It's a remarkable inversion, using the distant quasar not just as an object to study in itself, but as a tool to study everything between it and us. Now let's talk about what these objects have done to the universe. Because quasars aren't just record holders or curiosities, they've played active roles in shaping cosmic history. The universe you see around you, transparent, filled with ionized gas, pervaded by light from stars and galaxies, hasn't always been this way. For roughly 380,000 years after the Big Bang, the universe was opaque. It was a hot, dense plasma of protons, electrons, and photons, all in thermal equilibrium. Light couldn't travel far without scattering off free electrons. The universe was a glowing fog. Then the universe expanded and cooled enough that electrons and protons could combine to form neutral hydrogen atoms. This epoch is called recombination. The free electrons disappeared into atoms, photons stopped scattering, and the universe became transparent. The light from that transition is what we observe today as the cosmic microwave background. The relic radiation from recombination, now cooled to just 2.7 Kelvin by the universe's expansion. But transparency didn't mean brightness. The universe after recombination was dark. The first stars hadn't formed yet. There were no galaxies, no quasars, no light sources except the fading glow of the Big Bang itself. This period is called the Cosmic Dark Ages. It lasted for roughly 100 million years, maybe more. The universe was filled with neutral hydrogen gas, slowly collapsing under gravity to form the first structures, but producing no light. Then the first stars ignited. Population 3 stars, massive and hot, born from pristine hydrogen and helium. These stars emitted intense ultraviolet radiation. The UV photons had enough energy to ionize hydrogen, to strip the electron away from the proton, turning neutral atoms back into free charges. The first stars created small bubbles of ionized gas around them. When these stars died, exploding as supernovae, they enriched the surrounding gas with heavy elements. Second-generation stars formed, incorporating these elements. Galaxies assembled from the gravitational collapse of dark matter halos. And then the first quasars turned on. Quasars emit prodigious amounts of ultraviolet radiation. A single luminous quasar produces more ionizing photons than millions of stars combined. When a quasar lights up, it creates an expanding bubble of ionized gas, a Strömgren sphere, pushing outward into the surrounding neutral medium. Initially, these ionized bubbles were isolated. Pockets of ionized gas surrounding individual quasars or clusters of galaxies, separated by vast regions of neutral hydrogen. The universe was a patchwork, partially ionized, partially neutral. But as more quasars turned on and more stars formed, the ionized bubbles grew and began to overlap. The neutral regions shrank, the ionized regions merged, and at some point, probably between 700 million and 1 billion years after the Big Bang, the ionized bubbles percolated. They connected across the universe. The last pockets of neutral hydrogen were ionized. The transition was complete. This is reionization. The universe went from mostly neutral to mostly ionized. transparency transitioned from a local property around light sources to a global property of the cosmos, and quasars were key players in this process. We know this from several lines of evidence. One is the Lyman alpha forest I mentioned earlier, the absorption features in quasar spectra caused by neutral hydrogen along the line of sight. By studying how the Lyman alpha forest changes with redshift, we can trace the evolution of the neutral hydrogen fraction over cosmic time. At high redshifts, above redshift 6, we see strong Gunn-Peterson absorption. The quasar spectra show complete absorption blueward of the Lyman alpha emission line, indicating the presence of significant amounts of neutral hydrogen in the intergalactic medium. This is the signature of incomplete reionization. At lower redshifts, below redshift 6, the Gunn-Peterson absorption disappears. The spectra show the Lyman alpha forest of individual absorption lines, but no complete absorption trough. The intergalactic medium is highly ionized. The transition happens around redshift 6, corresponding to about 900 million years after the Big Bang. This is when reionization was completing. But quasars contribute more than just photons. Their feedback, the winds and jets I've described, also affects reionization. Quasar-driven winds can clear out gas from their host galaxies, reducing star formation. This might seem counterproductive for reionization. Fewer stars mean fewer ionizing photons, but it also redistributes gas into the intergalactic medium, where it can be more easily ionized by the pervasive radiation field. The jets from radio-loud quasars punch channels through the intergalactic medium, creating low-density paths that ionizing radiation can travel through more easily. These channels might help connect isolated, ionized bubbles, accelerating the percolation process. And the quasars themselves, by being the brightest sources of ionizing radiation, ensure that even low-density regions far from galaxies receive some ionizing flux. Stars ionize their immediate neighborhoods. Quasars ionize cosmological volumes. The relative contribution of stars versus quasars to reionization is still debated. Current consensus suggests stars did most of the work. There are simply more of them, and collectively they produce more ionizing photons. But quasars likely contributed at the 10 to 20% level, and in low-density regions far from galaxies, quasars might have been dominant. More importantly, quasars reionized helium. Hydrogen has one electron. Ionize it once, and you've stripped away that electron, but helium has 2 electrons. You can ionize it once, removing 1 electron, and it's still partially neutral. To fully ionize helium, you need to remove both electrons. The first ionization of helium, removing 1 electron, probably happened alongside hydrogen reionization. The same UV photons that ionize hydrogen can ionize helium once. But doubly ionizing helium requires higher energy photons, photons in the extreme ultraviolet, with energies above 54.4 electron volts. Stars don't produce many photons at these energies. Their spectra peak at lower energies, and the extreme UV is absorbed by intervening gas. Quasars, however, produce copious extreme UV radiation. Their accretion disks are hot enough, and their continuum spectra extend to high enough energies to doubly ionize helium efficiently. The reionization of helium happened later than hydrogen reionization, at redshifts around 3 to 4, roughly 2 to 3 billion years after the Big Bang. This is when the quasar population was most abundant and most luminous, the cosmic quasar era. We see the signature of helium reionization in the spectra of distant quasars, in the evolution of the helium-Lyman alpha forest. The transition from opaque to transparent in helium absorption happens around redshift 3, consistent with quasar-driven helium reionization. This matters because the ionization state of the intergalactic medium affects its temperature, its chemistry, and its ability to collapse into structures. Helium reionization heated the intergalactic medium, potentially affecting the formation of small galaxies at those epochs. Quasars didn't just illuminate the universe, they heated it. enriched it with metals blown out in winds, shaped the distribution of gas through feedback, regulated the growth of galaxies. Every galaxy, every structure, every star, everything you see in the universe today exists in a cosmos that was fundamentally altered by quasars during the first few billion years after the Big Bang. And we're only beginning to understand the full extent of their influence. The universe is not uniform. Look at any map of galaxy distribution and you'll see structure, filaments of galaxies stretching across hundreds of millions of light years, dense clusters where thousands of galaxies congregate, vast voids nearly empty of galaxies, walls and sheets of matter defining the boundaries between voids. This is the cosmic web, the large-scale structure of the universe, and quasars helped build it. Let me take you back to the early universe again, but this time focused not on individual objects, but on the distribution of matter across cosmic scales. After recombination, the universe was remarkably uniform. The cosmic microwave background shows this. The temperature variations across the sky are tiny, 1 part in 100,000. Those tiny variations represent density fluctuations in the early universe. Regions that were slightly denser than average, regions that were slightly less dense. Gravity amplifies these differences. Dense regions attract more matter, becoming denser. Underdense regions lose matter to their denser neighbours, becoming emptier. Over time, the contrast grows. The slight overdensities become significant concentrations of mass. The slight underdensities become voids. Dark matter dominates this process initially. It doesn't interact with radiation, so it can collapse freely while the ordinary matter is still coupled to photons. Dark matter forms the skeleton of cosmic structure, the halos into which galaxies will eventually form. But dark matter is invisible. We only know it's there through its gravitational effects. The visible universe, stars, gas, galaxies, is made of ordinary matter, and ordinary matter's evolution is more complicated. In the early universe, before reionization, ordinary matter could collapse into dark matter halos and cool efficiently. Gas falling into a halo would radiate away its thermal energy and settle into dense structures. Stars could form, galaxies could assemble. But after reionization, the situation changed. The intergalactic medium became ionized and hot, temperatures around 10,000 Kelvin. This thermal energy provides pressure support against gravitational collapse. Small dark matter halos, those with masses below about 1 billion solar masses, can no longer hold onto their gas. The thermal pressure is enough to resist the halo's gravity. The gas doesn't collapse. Stars don't form. This is called photoheating feedback. The ionizing radiation from stars and quasars doesn't just reionize the universe, it heats it, and that heating prevents small galaxies from forming. Quasars contribute to this heating. Their UV radiation ionizes and heats the intergalactic medium. Their winds inject additional thermal energy. The cumulative effect is to raise the temperature floor of the intergalactic gas. This has profound consequences for structure formation. Without photoheating, the universe would have formed many more small galaxies than we observe. The smallest halos would have collapsed their gas and formed stars. We'd see a galaxy mass function, the number of galaxies as a function of mass, that's much steeper at the low mass end. We don't see that. The observed galaxy mass function drops off at low masses faster than dark matter halo abundance would predict. There are fewer small galaxies than there should be based on dark matter alone. Photoheating explains this. Small halos are prevented from forming stars by the hot ionized intergalactic medium. Only halos massive enough to gravitationally bind the hot gas can form galaxies. Quasars are partly responsible for establishing this mass threshold. By contributing to reionization and ongoing photoheating, they've shaped the galaxy mass function. They've determined which halos become galaxies and which remain dark. Now let's talk about feedback on galaxy scales, because this is where quasars' influence is most direct and dramatic. I've mentioned the m-sigma relation, the tight correlation between black hole mass and the velocity dispersion of stars in the galaxy's bulge. This, Correlation is observational fact. Measure the properties of many galaxies, plot black hole mass versus sigma, and you get a remarkably tight relationship. Why does this correlation exist? The black hole is a tiny fraction of the galaxy's mass. It occupies an infinitesimal volume at the galactic centre. How does it know about the properties of the bulge, which is thousands of light years away? The answer is coevolution. The black hole and the galaxy grow together, regulated by feedback processes that couple them. Here's the scenario. A galaxy forms through the collapse and merger of smaller structures. Gas falls into the central regions. Stars form. A central black hole, possibly formed from population 3 stellar remnants or direct collapse, begins accreting. Initially, the black hole is small and relatively quiet, but as it accretes, it grows. Its luminosity increases. At some point, it becomes bright enough to significantly affect the surrounding gas. The quasar turns on. Radiation pressure from the accretion disk and energy injection from winds begin to push on the galaxy's gas. If the quasar is powerful enough, it can drive large-scale outflows, galactic winds carrying gas out of the galaxy at velocities exceeding the escape speed. This ejected gas is the fuel for future star formation. By removing it, the quasar is shutting down the galaxy's ability to make new stars. Star formation slows or stops entirely. The galaxy transitions from a star-forming blue galaxy to a passive red galaxy. Meanwhile, the quasar itself is running out of fuel. The gas that was feeding it is being blown away by its own radiation. The accretion rate drops. The quasar fades. The black hole enters a dormant phase. The galaxy now has a large bulge of old stars and a massive dormant black hole at its centre. The black hole's mass is proportional to the bulge mass because the feedback process regulated both. The black hole grew until it was powerful enough to shut off its own fuel supply and the galaxy's star formation. The result is the M-sigma relation. This is AGN feedback in action. It's a self-regulating process. The black hole can't grow indefinitely because its own radiation limits the gas supply. The galaxy can't form stars indefinitely because the quasar expels the necessary gas. Observationally, we see evidence of this feedback everywhere. Galactic winds are detected in many active galaxies. Molecular gas is observed streaming out of galactic nuclei at thousands of kilometers per second. The most massive galaxies, those with the biggest black holes, are almost all passive, with minimal ongoing star formation. There's an interesting asymmetry here. Small galaxies, those with relatively small black holes, can continue forming stars even if they host active galactic nuclei. The black hole isn't powerful enough to expel gas from the entire galaxy. Star formation continues in the outer regions, but massive galaxies, those with billion solar mass black holes, experience very effective quenching when the quasar is active. The feedback is strong enough to affect the entire galaxy. Once quenching occurs, these massive galaxies stay passive. They don't resume star formation because they've lost their gas reservoirs. This explains the red sequence on colour magnitude diagrams. Massive galaxies are red. They have old stellar populations and minimal star formation because quasar feedback has shut them down. Less massive galaxies are on the blue cloud. They're still forming stars because their feedback is weaker. The cosmic star formation history shows this too. Star formation in the universe peaked around redshift 2, about 10 billion years ago. Since then, the overall star formation rate has declined by more than an order of magnitude. Why did star formation decline? Partly because the universe's gas supply is being depleted, converted into stars or ejected from galaxies. But partly because quasar feedback became more effective. The quasar era, the epoch when quasars were most abundant and luminous, coincides with the peak of cosmic star formation. As quasars shut down star formation in massive galaxies, the cosmic star formation rate declined. Quasars are regulators, thermostats for galaxy growth. They prevent the most massive galaxies from growing too large by ejecting the gas those galaxies would otherwise use to form stars. Without this regulation, our models predict that massive galaxies would be much more massive than observed. They'd continue accreting gas and forming stars until they exhausted the available supply. The galaxy mass function would extend to much higher masses. We don't see that. There's an upper cutoff to galaxy mass. Galaxies more massive than a few trillion solar masses are extremely rare. This cutoff is almost certainly imposed by AGN feedback. Now let's talk about clusters, because quasars and their relativistic jets have effects on the largest, gravitationally bound structures in the universe. Galaxy clusters are the largest virialized objects, systems in gravitational equilibrium in the cosmos. They contain hundreds or thousands of galaxies, but most of their mass is in two components: dark matter, which dominates the total mass, and hot intracluster gas, which fills the space between galaxies. This intracluster gas, also called the intracluster medium or ICM, is incredibly hot. Temperatures range from 10 million to 100 million Kelvin. At these temperatures, the gas is fully ionized and emits X-rays. We observe clusters as extended X-ray sources. The ICM contains a substantial fraction of the cluster's baryon mass, the ordinary matter. In a typical rich cluster, there's more mass in the ICM than in all the galaxy's stars combined. This gas represents the cluster's reservoir for future star formation, at least in principle. But here's the problem. The gas should be cooling. The ICM emits X-rays through Bremsstrahlung radiation, thermal emission from hot plasma. This radiation carries energy away from the gas. As the gas radiates, it cools. And gas that cools will increase in density and radiate even more efficiently. This is a runaway process called a cooling catastrophe. If you let this process run unchecked, the ICM in cluster cores should cool rapidly, condense, and form enormous amounts of stars, hundreds to thousands of solar masses per year. The central galaxies and clusters should be forming stars prodigiously, fed by the cooling intracluster gas. They're not. Observations show star formation rates in central cluster galaxies are typically very low, a few solar masses per year at most, sometimes less. The cooling catastrophe isn't happening. Something is heating the ICM, preventing it from cooling, and that something is AGN feedback from the central galaxy's supermassive black hole. Nearly every massive cluster has a giant elliptical galaxy at its center. This brightest cluster galaxy, BCG, hosts a supermassive black hole, often in an active or recently active state. The black hole may not be shining as a brilliant quasar, but it's accreting at a low level and driving jets. These jets don't escape the cluster. They're not moving fast enough or carrying enough energy to blow through the cluster's gravitational potential. Instead, they inflate giant bubbles, cavities, in the ICM. You can see these bubbles in X-ray images of clusters, regions of reduced X-ray brightness, sometimes hundreds of thousands of light years across, carved out by the jets pushing aside the hot gas. The bubbles are filled with relativistic plasma, electrons and magnetic fields, but they're much less dense than the surrounding ICM, so they appear as dark spots in X-ray images. These bubbles inject energy into the ICM. As they inflate, they do work against the pressure of the surrounding gas. They drive shocks and sound waves, pressure waves travelling through the hot plasma at the speed of sound, which in this medium is thousands of kilometers per second. The energy from the bubbles, shocks and waves heats the ICM. Not uniformly, the heating is concentrated in the cluster core, but enough to offset the radiative cooling. The ICM reaches a quasi-equilibrium, where heating from AGN feedback balances cooling from X-ray emission. This is called radio mode feedback or maintenance mode feedback, because it's typically associated with radio loud AGN, and because its role is to maintain the ICM temperature rather than to expel gas from the cluster entirely. The energy budget works. We can measure the energy in the bubbles from their size and the pressure of the surrounding gas. We can measure the radiative cooling rate from the X-ray luminosity. The two balance. The AGN is injecting just enough energy to prevent catastrophic cooling, and this process is remarkably stable. The black hole accretes at a low rate, driving jets that heat the ICM. The heating reduces the cooling flow, limiting the gas supply to the black hole. The system self-regulates. If cooling increases, more gas reaches the black hole, it accretes more, the jets become more powerful, and heating increases. If heating overshoots, the gas supply is cut off, accretion drops, jets weaken, and cooling resumes. It's a thermostat, a self-regulating feedback loop operating across cluster scales. Without this feedback, clusters would look very different. Their cores would be filled with dense, cooled gas and vigorously forming stars. The central galaxies would be blue and actively star-forming rather than red and passive. We see the opposite. Cluster cores are hot and X-ray bright, but not forming many stars. Central galaxies are red and dead. AGN feedback explains this. Quasars, or more precisely, their lower luminosity AGN cousins, are preventing the formation of the most massive galaxies in the universe. They're keeping galaxy clusters from converting their gas into stars. They're shaping the properties of clusters across cosmic time. Let me tell you about a specific system, the Perseus cluster. It's one of the most massive galaxy clusters in the nearby universe, about 240 million light-years away. At its centre is the galaxy NGC 1275, hosting an active supermassive black hole. The black hole in NGC 1275 is driving jets that have inflated enormous cavities in the Perseus cluster's ICM. These cavities have been studied in exquisite detail with the Chandra X-ray Observatory. They're so large that the sound waves associated with them have the lowest frequency note ever detected from an object in the universe, a B-flat, 57 octaves below middle C, far below the threshold of human hearing. The total energy in the Perseus cluster's bubbles is around 10 to the 61 ergs, similar to the jet energy in Hercules A I mentioned earlier. This energy has been injected over roughly 100 million years, corresponding to an average power output of about 10 to the 45 ergs per second. That's a lot of power, but it's well below the Eddington luminosity for the central black hole. The black hole is accreting gently, not in a full quasar mode, but the cumulative energy over time is enormous, and the Perseus cluster isn't unique. Nearly every cluster with deep X-ray observations shows evidence of bubbles, cavities, and AGN feedback. It's a universal phenomenon in massive clusters. This feedback has been operating across cosmic time. We see evidence of it in clusters at high redshift, though the details change. Earlier clusters might have experienced more violent feedback episodes during the quasar era, while today's clusters are in a gentler maintenance mode. Now let's talk about something more subtle but equally important: how quasars affect the metal content of the universe. Metals, in astronomical parlance, means all elements heavier than hydrogen and helium. Carbon, oxygen, iron, silicon, everything on the periodic table except the two lightest elements. These metals are produced by stars through nucleosynthesis and dispersed when stars die, especially in supernova explosions. The early universe had no metals. The Big Bang produced only hydrogen, helium, and traces of lithium. The first stars, population 3, formed from this pristine gas. When they died, they enriched their surroundings with the first metals. Subsequent generations of stars incorporated these metals, produced more, and dispersed them through supernovae and stellar winds. Over cosmic time, the metal content of the universe has increased. The intergalactic medium, initially metal-free, has been polluted with metals ejected from galaxies. Quasars play a role in this metal enrichment, but not in the way you might think. Quasars don't produce metals, they're not stellar, they don't do nucleosynthesis, but they transport metals. The winds driven by quasar feedback can carry metal-enriched gas from the galaxy, where metals have been produced by stars, into the intergalactic medium. This gas has already been enriched by supernovae. The quasar wind launches it into intergalactic space, where it mixes with the pristine gas. We detect this metal enrichment by studying absorption lines in quasar spectra. The light from a distant quasar passes through intervening gas clouds, which imprint absorption features. By analysing these features, we can measure the metal content of the absorbing gas and how it varies with redshift and distance from galaxies. The results show that even gas far from galaxies, in the low-density regions of the intergalactic medium, contains metals. Not at the same level as gas in galaxies, but detectably enriched above the primordial composition. This widespread enrichment requires a transport mechanism. Metals produced in galaxies need to travel far into the intergalactic medium. Quasar-driven winds are one such mechanism. They can expel gas to distances of hundreds of kiloparsecs or more from the galaxy, carrying metals with it. Supernova-driven winds can also transport metals, but they're less effective at reaching large distances. Quasars, with their enormous energy output, can launch winds powerful enough to escape the galaxy's gravitational potential and pollute the surrounding intergalactic medium. There's also evidence that jets can transport metals. The lobes of radio galaxies sometimes show enhanced metal abundances, suggesting they've dredged up metal-enriched gas from the central galaxy and carried it to the cluster outskirts. The metal enrichment of the intergalactic medium matters because metals affect cooling. A gas cloud with metals can cool more efficiently than a pure hydrogen-helium cloud, because metal lines provide additional pathways for radiating energy. This affects the ability of gas to collapse and form stars. Paradoxically, quasars both suppress and enable star formation. They suppress it through photoheating and wind-driven ejection of gas. But by enriching the intergalactic medium with metals, they might enhance cooling in certain environments, potentially facilitating star formation in some contexts. The interplay is complex. The net effect depends on the balance between these competing processes and varies across different environments and cosmic epochs. Let me shift to something more speculative but fascinating: the possibility that quasars affected the formation of the first structures in the universe. There's a phenomenon called Lyman-Werner feedback. Lyman-Werner photons are ultraviolet photons with energies between 11.2 and 13.6 electron volts. They're energetic enough to dissociate molecular hydrogen, H2, but not energetic enough to ionize atomic hydrogen. Molecular hydrogen is crucial for star formation in the early universe. In the absence of metals, H2 is the primary coolant. Gas clouds need to radiate away their thermal energy to collapse and form stars, and in metal-free gas, H2 provides the most efficient cooling, but Lyman-Werner photons destroy H2. If a gas cloud is irradiated by a strong Lyman-Werner background, the H2 is photodissociated, cooling becomes inefficient, and star formation is suppressed. Early quasars produce copious Lyman-Werner radiation. Their UV spectra extend into the Lyman-Werner band, and because they're so luminous, a single quasar can affect large volumes of surrounding space. This might have delayed the formation of small galaxies in the vicinity of the first quasars. Regions near quasars would have a suppressed H2 content, inefficient cooling, and reduced star formation. Ironically, the first quasars might have created voids in the small galaxy population around them, but there's a flip side. If Lyman-Werner feedback suppresses fragmentation, prevents a collapsing gas cloud from breaking into small pieces, it might promote the formation of more massive objects. Instead of fragmenting into many small stars, a cloud, irradiated by Lyman-Werner photons, might collapse into a single massive object or a massive black hole seed. This could be a mechanism for forming the massive seed black holes needed to explain early quasars. The first quasars create conditions conducive to forming the next generation of massive seeds, which grow into the next generation of quasars. It's a self-propagating process. Quasars create the conditions for more quasars. Over time, this could lead to a population of supermassive black holes distributed throughout the universe, all descended from the first quasars. This is speculative. We don't have direct observational evidence for this process yet, but it's a plausible scenario that connects quasar feedback to black hole formation in interesting ways. let me tell you about gravitational waves, because quasars, or more precisely merging supermassive black holes, will be sources of low-frequency gravitational radiation. When two galaxies merge, their central black holes eventually sink to the centre of the merge system through a process called dynamical friction. The black holes plough through the surrounding stars and gas, losing orbital energy and angular momentum spiralling inward. At some point, the two black holes form a binary system. They're orbiting each other, separated by distances that might initially be parsecs but decrease over time. If the binary is tight enough, separated by less than a parsec, it can shrink further through gravitational wave emission. The orbital motion of the two black holes generates gravitational radiation, which carries away energy and angular momentum. The orbit decays, the black holes spiral closer. Eventually they merge. The final plunge and merger happens quickly, releasing an enormous burst of gravitational waves. The merged black hole rings down, oscillates and settles into a stable configuration, emitting additional gravitational radiation as it does. The gravitational waves from supermassive black hole mergers have frequencies in the nanohertz to millihertz range, far too low for ground-based detectors like LIGO to sense. LIGO is sensitive to frequencies around 100 Hz, corresponding to stellar mass black hole mergers. Detecting gravitational waves from supermassive black holes requires space-based detectors or pulsar timing arrays. Pulsar timing arrays use an array of pulsars, rapidly rotating neutron stars that emit regular pulses of radio emission, as a galaxy-sized detector. Gravitational waves passing through the Milky Way will slightly stretch and compress space-time, affecting the arrival times of pulses from distant pulsars. By monitoring many pulsars over years and looking for correlated variations in their pulse arrival times, we can detect the cumulative background of gravitational waves from supermassive black hole mergers across the universe. Several pulsar timing array collaborations, NanoGrav, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, have recently announced evidence for a gravitational wave background at nanohertz frequencies. The signal is consistent with expectations for a population of merging supermassive black hole binaries. This is extraordinary. We're detecting the gravitational hum of supermassive black holes merging across cosmic time. Every merger adds to the background. The cumulative effect is a stochastic gravitational wave signal pervading the universe, and some of these merging black holes might be powering quasars. If a binary black hole system is accreting gas, both black holes might be active. The system could appear as a dual AGN, or, if the binary is very tight, as a single quasar with peculiar variability or spectral properties. We've found candidate binary black hole systems in quasars, objects showing periodic variations in brightness, or with double-peaked emission lines suggesting two broadline regions orbiting each other. These are rare, but they exist. When LISA launches, a space-based gravitational wave detector planned for the 2030s, it will detect individual supermassive black hole mergers out to high redshifts. It will be able to localize them on the sky well enough that optical telescopes can identify the host galaxies. Imagine this. A gravitational wave signal is detected from a merging black hole binary at redshift 4. LISA provides coordinates. Optical telescopes observe that position and find a quasar. We see the quasar in light and detect the merger in gravitational waves. Multi-messenger astronomy for supermassive black holes. This will let us study the merger process in unprecedented detail. Gravitational waves tell us about the masses and spins of the black holes, the orbital dynamics, the final ring down. Electromagnetic observations tell us about the gas environment, the accretion rates, the feedback effects. Together, they'll provide a complete picture of how supermassive black holes merge and what happens to the surrounding matter. Quasars are not static objects frozen in time. They're evolving systems, the products of cosmic history, and participants in ongoing processes. The quasars we observe today are snapshots, moments in the long lives of galaxies and black holes. Some quasars are young, recently turned on by a galaxy merger that funneled gas to the central black hole. They're bright, rapidly accreting in the first flush of their active phase. Others are old, near the end of their fuel supply. They're fading, their accretion rates declining, on the verge of shutting off and becoming dormant. Some are in between, in a steady state where accretion is sustained by ongoing processes in the galaxy. Slow infall of gas, minor mergers, capture of gas clouds. And some are in transition, changing from one state to another. The changing look quasars I mentioned earlier, transforming on human timescales. Each quasar's history is written in its properties. Its luminosity tells you its current accretion rate. Its spectrum tells you about the structure and composition of the accreting material. Its variability tells you about the size and dynamics of the emission region. Its host galaxy tells you about the environment and merger history. By studying populations of quasars, how their properties vary with redshift, environment, galaxy type, we can piece together the evolutionary pathways. We can understand how quasars turn on and off, how they correlate with galaxy mergers, how their activity depends on fuel supply and feedback. This is cosmic archaeology, using present-day observations to infer past processes, reconstructing history from the evidence left behind, and the picture that emerges is one of deep connection. Quasars and galaxies are not separate phenomena, they're intertwined. The growth of supermassive black holes is coupled to the growth of galaxies. Quasar feedback regulates star formation. Galaxy mergers trigger quasar activity. The cosmic web funnels gas that feeds both stars and black holes. You cannot understand the universe's large-scale structure without understanding quasars' role in shaping it. You cannot understand galaxy evolution without accounting for AGN feedback. You cannot explain the distribution of metals, the thermal state of the intergalactic medium, or the galaxy mass function without including quasars in the model. They're integral, essential components of the cosmic ecosystem, and they're everywhere, or at least their effects are. Even dormant black holes, the vast majority of supermassive black holes in the present-day universe, were probably once quasars. They grew through accretion, shaped their host galaxies through feedback, then faded when the fuel ran out. Your own galaxy's central black hole, Sagittarius A, was almost certainly active in the past. Billions of years ago, the Milky Way might have hosted a quasar. The galactic center would have been brilliant, outshining the combined light of all the galaxy's stars. That quasar faded long before the Sun formed, but its legacy remains. The Milky Way's structure, its gas content, its star formation history, all were influenced by past episodes of black hole activity. Every massive galaxy has been through this cycle. Active phases and dormant phases, feeding and starvation, brightness and darkness. Quasars are a phase, a temporary state, but a crucial one that shapes the final product. Let me tell you about TON 618, because it represents something close to the absolute limit of what the universe permits. TON 618 is a quasar located roughly 10.8 billion light-years away, at a redshift of 2.219. We're seeing it as it was when the universe was roughly a quarter of its current age. At that epoch, the cosmic star formation rate was near its peak. Galaxies were actively forming stars, mergers were common, conditions were ideal for feeding supermassive black holes, and TON 618 took full advantage of those conditions. The black hole at the centre of TON 618 has an estimated mass of approximately 66 billion solar masses. Let me pause on that number. 66 billion. That's 10,000 times more massive than Sagittarius A, the black hole at the centre of our Milky Way. It's 10 times more massive than the black hole in M87. If you replace the Sun with TON 618's black hole, the event horizon would extend well beyond the orbit of Neptune. The Schwarzschild radius, the radius of the event horizon, would be about 1/300 astronomical units. For comparison, Pluto's average distance from the Sun is about 40 AU. The event horizon of this black hole is 30 times larger than Pluto's orbit. At its peak, TON 618 had a luminosity estimated at around 4 × 10 to the 41 watts, making it one of the most luminous objects ever observed. It's since faded somewhat. Quasars vary. But at maximum brightness, it was outputting the energy equivalent of 140 trillion suns. How does a black hole become this massive? The standard growth mechanisms we've discussed, Eddington-limited accretion over billions of years, can potentially explain it, but barely. You need to start with a massive seed, accrete almost continuously at high rates, and avoid too much feedback-driven quenching. TON 618 probably grew through multiple major galaxy mergers. Each merger delivered a fresh supply of gas to the central black hole. The black hole consumed this gas voraciously, growing by billions of solar masses with each feeding episode. Over cosmic time, these mergers accumulated, building the monster we observe today. But there's a limit to how massive black holes can grow, and TON 618 is approaching it. The limit isn't imposed by gravity. Black holes can theoretically be arbitrarily massive. The limit comes from feedback. As a black hole becomes more massive, its Eddington luminosity, the maximum brightness it can sustain, scales with mass. A more massive black hole can shine brighter without, blowing away its fuel supply. But there's a catch. The galaxy hosting the black hole has a finite gravitational potential. There's a maximum radiation pressure the galaxy can withstand before gas is ejected entirely. At some black hole mass, the Eddington luminosity becomes so large that even accreting at a fraction of the Eddington rate produces enough radiation to expel all the gas from the galaxy. Theoretical calculations suggest this maximum black hole mass is around 50 to 100 billion solar masses, depending on the galaxy's properties. TON 618 is right at this limit. It's probably near the end of its growth phase. Its feedback is so powerful that it's clearing out the surrounding gas, shutting off its own fuel supply. If TON 618 continues to accrete, it might grow slightly larger, but not much. Eventually the feedback will dominate, gas will be expelled, and the quasar will fade. The black hole will enter a dormant phase, massive and dark, lurking at the centre of a gas-poor galaxy. This is the fate of the most massive black holes. They grow until their own brilliance prevents further growth. They hit a ceiling imposed by physics, not by lack of fuel, but by the consequences of their own power. And TON 618 isn't alone at these extreme masses. There are other candidates. ICL 101's central black hole has an estimated mass of around 40 to 100 billion solar masses, though measurements are uncertain. Holmberg 15A hosts a black hole of roughly 170 billion solar masses, though this estimate is highly disputed and might be an overestimate. The point is, the universe has produced black holes at or near the theoretical maximum mass. These objects are rare, we've only found a handful, but they exist. The universe explored the parameter space and pushed to the limits. Now let me tell you about something even stranger. A quasar with no detectable host galaxy. This sounds impossible. Quasars are supposed to be powered by supermassive black holes at the centres of galaxies. No galaxy, no black hole, no black hole, no quasar. The logic is airtight, except we found one. The object is called HE 04502958, and it baffled astronomers when it was discovered and analysed in detail with Hubble and other telescopes. It's a quasar at moderate redshift, clearly active with all the spectroscopic signatures of a feeding black hole. But when astronomers looked for the host galaxy, the collection of stars that should surround the quasar, they found nothing. At the quasar's location, there's no stellar light, no galaxy, just the quasar itself shining in isolation. This violates everything we know about quasars. How can a supermassive black hole exist without a galaxy to host it? Where did the black hole come from? What is it accreting if there's no surrounding reservoir of gas and stars? For years, this was a genuine mystery. Theories proliferated. Maybe the host galaxy was there but completely obscured by dust, rendering it invisible in optical wavelengths. Maybe the quasar's light was overwhelming the galaxy's starlight. making the galaxy too faint to detect. Eventually, more detailed observations provided an answer, though not a simple one. It turns out there is a galaxy nearby, a companion galaxy about 22,000 light-years away from the quasar. This companion is actively forming stars at a high rate, and it shows signs of recent interaction or merger. The best current explanation is that He 0450-22958 is the remnant of a galaxy merger, and the quasar is located in a region of the merger where the stellar component was ejected or dispersed during the collision. The black hole remained because black holes, being extremely compact and massive, are harder to eject than stars. The stars were flung out by tidal forces during the merger, but the black hole stayed put, or at least stayed near the centre of mass of the system. It's still accreting gas from the merger debris, which is why it's active as a quasar, so there is a host galaxy, or at least there was. The galaxy was destroyed or disrupted by the merger, and what remains is a naked quasar, a black hole without the typical surrounding stellar population. This is rare. Most quasars reside in intact galaxies, but He 0450-29558 shows that under extreme conditions, violent mergers perhaps, the usual structure can be disrupted. You can have a quasar without an obvious host, at least temporarily. This matters because it tells us that galaxy mergers can be incredibly destructive. They don't just trigger quasar activity, they can tear apart the galaxies themselves. The final product of a merger might look very different from the progenitor galaxies, and it raises questions about what happens to the black hole after the quasar phase ends. If the stellar component of the galaxy has been dispersed, does the black hole remain isolated? Does it wander through intergalactic space, a rogue, supermassive black hole with no galactic home, or does it eventually merge with another galaxy, sink into the centre of a new host through dynamical friction? We don't know. He 0450-27958 might be showing us a brief transitional state, a snapshot of a process that eventually leads to the black hole being captured by another system. Let me tell you about the fastest spinning black holes we've measured, because spin is a fundamental property that tells us about growth history. Black holes have only a few properties: mass, spin, and electric charge. Charge is generally negligible for astrophysical black holes. They're electrically neutral for all practical purposes. That leaves mass and spin. Spin is quantified by a dimensionless parameter called A, which ranges from 0, non-spinning, to 1, maximally spinning. A black hole with E equals 1 is rotating at the fastest rate allowed by general relativity. Any faster, and it would violate the cosmic censorship conjecture. It would create a naked singularity which most physicists believe isn't possible. Measuring spin is challenging. We can't observe the black hole directly. Instead, we measure the effects of spin on the surrounding accretion disk and the light it emits. The innermost stable circular orbit, the ISCO, around a black hole depends on the black hole's spin. For a non-spinning black hole, the ISCO is at 6 gravitational radii. For a maximally spinning black hole, it's at 1 gravitational radius, much closer to the event horizon. The accretion disk extends down to the ISCO. Inside the ISCO, orbits are unstable, and matter quickly plunges into the black hole without emitting much additional radiation. So the inner edge of the disk, the boundary between stable emission and final plunge, is determined by the ISCO, which depends on spin. By measuring the spectrum of X-rays from the inner disk, particularly the relativistically broadened ion emission line, we can infer the location of the inner edge. This tells us the ISCO radius, which tells us the spin. Many quasars show evidence of high spin. Values of a greater than 0.9 are common. Some measurements suggest spins very close to maximal, a greater than 0.98 or even 0.99. High spin tells us these black holes grew through prolonged coherent accretion. If a black hole accretes from a disk that's aligned in a single direction over long periods, the accretion torques the black hole, spinning it up. Over time, the spin approaches the maximum value. Conversely, if a black hole grows through chaotic accretion from randomly oriented directions, or through mergers with other black holes that might be spinning in different directions, the spin averages out, The final spin is lower. The fact that many quasars have high spin suggests their growth was relatively orderly. They accreted from coherent disks, aligned over billions of years. This is consistent with a picture where supermassive black holes grow primarily through gas accretion rather than mergers. Mergers probably happen, we've detected gravitational wave backgrounds from them, but they might not be the dominant growth channel. Most of the mass might come from gas. There are exceptions. Some black holes have low measured spins. These might have grown through more chaotic processes, or they might have spun down due to interactions with their disks or environments. The diversity of spins tells us there's diversity in growth histories. The fastest spinning quasar black holes are fascinating because they're maximizing a fundamental property. They're exploiting the full parameter space allowed by general relativity. And their rapid spin has consequences. Frame dragging is strongest for high-spin black holes, and the efficiency of energy extraction via the Blandford-Znajek process scales with spin. A maximally spinning black hole is a more efficient engine than a slowly spinning one. It can extract more energy from infalling matter. This might explain why some quasars are so luminous. They're powered by black holes that are not only massive but also rapidly spinning. Let me tell you about peculiar spectral features, because some quasars show anomalies that challenge our understanding. Most quasar spectra are relatively straightforward to interpret. You see broad emission lines from the broad line region, narrow lines from the narrow line region, a power law continuum from the accretion disk and corona, maybe some absorption features from intervening gas along the line of sight. But some quasars are weird. There's a class of objects called broad absorption line quasars, BAL quasars. These show deep, broad absorption features blue shifted relative to the emission lines. The absorption is coming from gas that's flowing outward at velocities of tens of thousands of kilometers per second. These are winds, powerful outflows driven by radiation pressure from the quasar, carrying matter away from the black hole at a significant fraction of the speed of light. The absorbing gas is between us and the quasar, blocking some of the light and creating the absorption features. BAL quasars are thought to represent a specific orientation and evolutionary stage. We're viewing them at an angle where we can see the wind, and the wind is dense and fast enough to produce strong absorption. In the unified model, BAL quasars might be systems where we're looking nearly edge-on through the equatorial wind, which is thicker and denser than the polar wind. Or they might represent a young phase of quasar evolution, where the black hole is still surrounded by dense gas, and the wind is just beginning to clear out the surrounding material. Over time, as the wind expels more gas, the system might transition to a more typical quasar appearance. Some BAL quasars show extreme velocities, outflows reaching 30,000 kilometers per second, 10% of the speed of light. These are among the most energetic winds in the universe. The mass loss rates can be hundreds of solar masses per year, comparable to or exceeding the accretion rate onto the black hole. This means the quasar is blowing away more mass than it's consuming. It's inefficient as a growth mechanism. Most of the available gas is being expelled rather than accreted. But this inefficiency is precisely the point of feedback. The quasar is shutting off its own fuel supply and the galaxy's star formation. Then there are quasars with anomalous emission line ratios. The relative strengths of different emission lines depend on the ionization state, density, and temperature of the emitting gas. By measuring line ratios, we can infer physical conditions. Most quasars cluster in a specific region of diagnostic diagrams, plots of one line ratio versus another. This defines the typical quasar locus, but some objects lie outside this region. Their line ratios are inconsistent with standard photoionization models. Why? Maybe the ionizing spectrum is unusual, harder or softer than typical. Maybe the gas density is extreme. Maybe there's additional heating from shocks rather than just photoionization. Maybe the geometry is peculiar. These anomalous quasars are rare, but they're informative. They show us that the standard model, while broadly correct, doesn't capture every system. There's diversity in quasar properties that we're still working to understand. Some quasars show time-variable spectral features. The The emission lines change strength or shape over timescales of months to years. This variability is expected. We know quasars vary, but in some cases the changes are dramatic. There are quasars that have transitioned from showing strong broad lines to showing no broad lines at all, as I mentioned with changing look quasars. The broad line region appears to have disappeared, possibly because the ionizing flux dropped below the threshold needed to sustain it. And then there are quasars with double-peaked emission lines. The broad lines are not single peaks but show two distinct peaks, separated by thousands of kilometers per second. This can happen if the broad line region is a rotating disk viewed close to edge-on. The two peaks correspond to the two sides of the disk, one side approaching us, blue shifted, the other receding, red shifted. Or it can indicate a binary black hole system, two black holes, each with its own broad line region, orbiting each other. The two sets of lines are Doppler shifted by their orbital motion, creating double peaks. Distinguishing between these scenarios is difficult. Monitoring over time can help. A binary system might show periodic changes as the black holes orbit, while a disk viewed edge-on would be more stable. But the timescales are long and observations are sparse. We've identified several candidate binary black hole quasars based on double-peaked lines or periodic variability. None are confirmed with absolute certainty. It's hard to rule out alternative explanations, but the population exists and future observations will characterize them better. Let me talk about what happens at the very end of a quasar's life, the transition from active to dormant. When a quasar runs out of fuel, or when feedback expels the remaining gas, the accretion rate drops, the luminosity declines. The broadline region, no longer sustained by intense ionizing radiation, dissipates. The quasar fades. This transition might happen quickly, on timescales of thousands to tens of thousands of years, or more slowly depending on how the fuel supply is cut off. If a wind suddenly expels all the gas, the transition is abrupt. If the fuel supply dwindles gradually, the fading is gentler. Eventually the quasar becomes undetectable. The black hole is still there, massive as ever, but no longer accreting significantly. It's dormant. The host galaxy transitions from an active galaxy to a passive one. Star formation, suppressed by quasar feedback, remains low or ceases entirely. The galaxy reddens as its stellar population ages and the blue massive stars die off. This is the state most massive galaxies are in today. Passive red ellipticals with dormant supermassive black holes. They went through a quasar phase billions of years ago, grew their black holes, expelled their gas, and have been quiet ever since. But dormancy isn't necessarily permanent. If new gas becomes available, perhaps from a minor merger, or from cooling of the hot halo gas in a cluster, or from the capture of a gas-rich dwarf galaxy, the black hole can reactivate. Low-level accretion might resume. The black hole might not become a full-fledged quasar again. It might accrete at a much lower rate, appearing as a low-luminosity AGN or LINA, low ionization nuclear emission region. These objects are common in nearby galaxies. They're powered by black holes accreting at a tiny fraction of the Eddington rate, producing modest luminosities. Some galaxies might go through multiple cycles: quasar phase, dormancy, low-level activity, dormancy again, perhaps another quasar phase if a major merger delivers fresh fuel. The duty cycle, the fraction of time spent in each state, depends on the galaxy's environment and merger history. Our own Milky Way's black hole, Sagittarius Ischium, is probably cycling through low-level activity. It accretes material sporadically, the occasional gas cloud or star that wanders too close, producing brief flares of emission. But it's not in a sustained active state. It's dormant most of the time, with occasional burps of activity. In the distant future, when the Milky Way merges with Andromeda, an event predicted to occur in about 4.5 billion years, the central black holes of both galaxies will eventually merge. The merger will likely deliver gas to the combined black hole, possibly triggering a quasar phase in the merged galaxy. For a brief period, cosmically speaking, the merger remnant might host an active quasar. Then, as the fuel is exhausted or expelled, the quasar will fade. The final product will be a large elliptical galaxy with a dormant black hole of roughly 9 million solar masses, the sum of Sagittarius A and Andromeda's central black hole. This future quasar will be billions of years from now. Earth, if it still exists, will likely be uninhabitable due to the Sun's evolution. But the quasar will shine briefly, adding its light to the cosmos before fading into the growing population of passive galaxies. The universe's future is quieter. The quasar era, the epoch of maximum quasar abundance and luminosity, is in the past, at redshifts around 2 to 3. Today, quasars are rarer. The universe has less available gas. Galaxies are more spread out, mergers less frequent. The conditions that create quasars are less common. In the far future, as the universe continues expanding and galaxies become more isolated, quasars will become rarer still. Eventually, the last quasar will fade. The last supermassive black hole will consume its last meal, and the universe will enter an era where all the black holes are dormant, dark, invisible, except through their gravitational effects. But that's trillions of years away. For now, quasars still exist. They're rarer than they were at cosmic noon, but they're still out there, feeding, shining, shaping their environments. Let me tell you about the role quasars will play in future cosmology, because they're not just objects of historical interest, they're tools for probing the universe's structure and evolution. One application is using quasars as tracers of large-scale structure. Quasars are biased tracers. They preferentially form in overdense regions where galaxies are abundant and gas is plentiful. By mapping the distribution of quasars across the sky and measuring their clustering, we can learn about the underlying distribution of dark matter. The Sloan Digital Sky Survey and its successors have catalogued hundreds of thousands of quasars, creating three-dimensional maps of their positions in space. These maps reveal the cosmic web, the filaments, clusters and voids that define large-scale structure. By analysing quasar clustering and comparing it to theoretical predictions, cosmologists can constrain parameters like the matter density of the universe, the amplitude of primordial density fluctuations, and the nature of dark energy. Quasars are also used to measure the expansion history of the universe through the Alcock-Paksinski test. This test uses the fact that the apparent clustering of objects depends on the cosmological model. If you assume the wrong cosmology, the clustering will appear anisotropic, different in the radial and transverse directions. By measuring the clustering and finding the cosmology that makes it isotropic, you can constrain cosmological parameters. This is a geometric test, independent of the specific properties of quasars. It depends only on their positions, not their intrinsic brightness or other characteristics. Another application is baryon acoustic oscillations, BAO. These are imprints of sound waves in the early universe, frozen into the distribution of matter when the universe became neutral. The characteristic scale of BAO, about 150 megaparsecs, provides a standard ruler that can be used to measure cosmological distances. By measuring BAO in the clustering of quasars, we can trace the expansion history of the universe across cosmic time. This constrains dark energy and tests models of cosmic acceleration. Quasars are particularly useful for BAO measurements at high redshift, where other tracers like galaxies become too faint to detect in large numbers. Quasars, being intrinsically bright, can be seen to much greater distances, extending BAO measurements into earlier epochs. The Lyman alpha forest, those absorption lines in quasar spectra, can also be used for BAO measurements. The forest traces the distribution of neutral hydrogen along the line of sight. By measuring correlations in the forest across many quasars, we can detect BAO in the three-dimensional distribution of gas. This is called Lyman alpha forest BAO, and it's been successfully measured by surveys like BOSS and eBOSS. It provides constraints on the expansion history at redshifts 2 to 3, an epoch that's difficult to probe with other methods. Quasars are also used to test fundamental physics. The fine structure constant, alpha, which determines the strength of electromagnetic interactions, is predicted to be constant across space and time in standard physics. But some theories suggest it might vary. By measuring the wavelengths of absorption lines in quasar spectra and comparing them to laboratory values, we can search for variations in alpha. If alpha were different in the distant past or in distant regions of space, the absorption lines would be shifted in predictable ways. Decades of measurements have found no convincing evidence for variation in alpha. The fine structure constant appears to be truly constant, at least to the precision we can currently measure. This rules out some exotic theories and supports the standard model of particle physics. But the search continues. More precise measurements, using more distant quasars and better spectroscopy, might reveal subtle variations that current data can't detect. Quasars also constrain the epoch of reionization, as I discussed earlier. By finding quasars at the highest redshifts and measuring the Gunn-Peterson absorption in their spectra, we can map when and how reionization proceeded. Future surveys will find quasars at even higher redshifts, perhaps beyond redshift 10, probing the universe when it was less than 500 million years old. These quasars will show us the universe in transition, as the first galaxies assembled and the first black holes grew. And quasars are targets for future missions. The James Webb Space Telescope is finding and characterizing high redshift quasars. Future telescopes, the extremely large telescope, the 30-meter telescope, will observe them in unprecedented detail. Space-based missions like LINX, a proposed X-ray observatory, would study the coronae and inner accretion disks of quasars with much higher sensitivity and resolution than current X-ray telescopes. And gravitational wave detectors, LISA and pulsar timing arrays, will detect supermassive black hole mergers, some of which might involve quasars. The future of quasar studies is bright. We're entering an era of multi-messenger, multi-wavelength observations. We'll combine electromagnetic data with gravitational waves. We'll observe quasars from radio to gamma-ray wavelengths simultaneously. We'll probe their structure on scales from the event horizon to the host galaxy. Every new observation will refine our models. Every new detection will test our theories. And the quasars, patient and indifferent, will continue to broadcast their information across the cosmos, waiting for us to decode it. You've journeyed far now. Across 2 explorations of quasars, you've travelled from discovery to understanding, from mechanism to consequence. You've seen how confusion yielded to clarity, how mysterious points of light became comprehensible physical systems. And you've witnessed the extremes, the records that define what the universe permits, the roles quasars play in cosmic history. Let me bring this to a close by talking about what all of this means. Not the physics, we've covered that. Not the observations, those too. But the deeper implications. What does it mean that the universe contains such objects? What does their existence tell us about the nature of reality? Start with scale. The human mind evolved to navigate a world of medium-sized objects at medium speeds. Trees, rivers, animals, other humans. We're not built to intuitively grasp the very small or the very large. Quantum mechanics feels weird because it operates on scales far below our experience. Cosmology feels abstract because it deals with distances and times far beyond what we encounter. Quasars force us to confront scale in its most extreme manifestation. A single quasar, a region smaller than our solar system, outshining a galaxy of hundreds of billions of stars. A black hole converting matter to energy at 10% efficiency, the most efficient process permitted by known physics. Jets accelerating particles to 99% of light speed, and maintaining that acceleration across distances of millions of light years. These aren't just big numbers, they represent physics pushed to fundamental limits, the universe exploring the boundaries of what's possible under its own laws. And the records, the most distant, most luminous, most massive, these are the universe testing those boundaries. finding the edges, discovering what happens when you take gravity, matter and energy and let them interact in the most extreme configurations. TON 618's 66 billion solar mass black hole isn't just impressive, it's a statement about limits. The universe can create objects this massive, but probably not much more massive. Feedback becomes too powerful. Self-regulation kicks in. There's a ceiling, and TON 618 is near it. The earliest quasars are those existing less than 700 million years after the Big Bang, aren't just distant. They're anomalies, puzzles that demand explanation. The universe created supermassive black holes faster than our models easily allow. Either our models are incomplete, or we're missing formation channels, or the universe found tricks we haven't thought of. These objects challenge us. They force us to refine our theories, to reconsider our assumptions, to push our understanding further. And that's exactly what science is for. Not to arrive at final answers, but to continually test and refine our models against reality. To use observations as constraints, narrowing the range of viable theories until we converge on truth, or at least closer, approximations of truth. Quasars are laboratories for this process. They exist at extremes where our theories become uncertain. Strong gravity, high energies, relativistic speeds, magneto-hydrodynamic turbulence, radiative transfer in complex geometries. Each aspect tests a different piece of physics, and getting all the pieces to work together consistently is hard. But we're doing it, slowly, imperfectly, with many uncertainties remaining, but we're making progress. 60 years ago, quasars were complete mysteries. Today, we understand the basic mechanism and many of the details. We can calculate their properties, predict their behavior, explain their evolution. We're not finished. There are still puzzles, but we've come extraordinarily far. Now consider the role quasars have played in cosmic history. They're not passive observers. They're active participants, agents of change. They reionize the universe, transforming it from an opaque neutral medium to the transparent ionized cosmos we observe today. Without reionization, the universe would look fundamentally different. Light couldn't travel freely, galaxies would be shrouded, the cosmic web would be invisible. They regulated galaxy formation through feedback. Without AGN feedback, the most massive galaxies would be much larger than observed. The galaxy mass function would extend to higher masses. The cosmic star formation history would be different. They enriched the intergalactic medium with metals, affecting the cooling and chemistry of gas across the universe. They heated the intergalactic medium, preventing small halos from forming galaxies. They shaped the large-scale structure through their influence on gas distribution and galaxy evolution. Every galaxy, every star, every planet, everything that exists in the present-day universe exists in a cosmos that was shaped by quasars. And this includes you. The atoms in your body were forged in stars, yes, but those stars formed in galaxies whose properties were determined in part by quasar feedback. The galaxy you inhabit, the Milky Way, went through its own quasar phase billions of years ago. Its current structure, its gas content, its stellar populations, all were influenced by that ancient episode of black hole activity. You exist in a universe where supermassive black holes grew and fed and shaped their surroundings. A universe where the brightest lights in cosmic history were engines of destruction and creation simultaneously. Where matter spiraled into oblivion while radiating enough energy to affect galactic and intergalactic scales. This is your universe. A cosmos where gravity's ultimate expression, the black hole, plays a central role in structure formation and evolution. Let me talk about the future, both cosmic and observational. Cosmically, quasars are fading into history. The peak of quasar activity was billions of years ago. Today, quasars are rarer. The universe has less available gas, fewer mergers, conditions less conducive to feeding supermassive black holes. In the far future, the last quasar will fade. Star formation will cease as galaxies exhaust their gas. The universe will darken as stars die, and no new ones form. Eventually, on timescales of trillions of years, even stellar remnants will fade or be consumed by black holes. The black holes themselves, those monuments to gravity's victory, will persist longer than anything else. But even they aren't eternal. Stephen Hawking showed that black holes evaporate through quantum processes, radiating away their mass over unimaginably long timescales. A solar mass black hole would take 10 to the 67 years to evaporate. A supermassive black hole like TON 618 would take 10 to the 100 years or more. These timescales are so vast they make the current age of the universe, a mere 13.8 billion years, seem like an eye blink. But eventually, even the black holes will disappear. The universe will be left with nothing but diffuse radiation and isolated particles separated by ever-expanding distances, approaching a state of maximum entropy. That's the heat death of the universe, the final state, the end of all complexity, the triumph of entropy. But that's so far in the future it's almost meaningless to contemplate. For now, for the next trillions of years at least, structure persists, galaxies exist, stars shine, black holes lurk in galactic centres, some still accreting, most dormant but patient, and we, briefly, exist to observe and understand it all. Observationally, the future is bright. We're entering a golden age of multi-wavelength, multi-messenger astronomy. Telescopes across the electromagnetic spectrum, gravitational wave detectors, neutrino observatories, all working together to probe the universe in unprecedented detail. The quasars we'll discover in the next decades will be more distant, more extreme, more puzzling than anything we've found so far. JWST is already pushing the boundaries, finding quasars at redshifts we didn't expect, with properties that challenge our models. Future telescopes will go further. They'll resolve accretion disks directly, image the bases of jets, measure black hole spins with precision, detect gravitational waves from mergers, and track variability in real time. Every observation will add detail to the picture. Every detection will test our theories, and some observations will surprise us, presenting phenomena we didn't predict, forcing us to expand our understanding. This is the nature of exploration. You venture into the unknown expecting to find what you're looking for, and instead, you discover things you didn't know to look for. The universe is under no obligation to match our expectations. It simply is, and our job is to observe and understand it as best we can. Quasars have been teachers in this process. They've revealed physics at extremes. They've shown us how the universe behaves when gravity dominates, when energy densities are enormous, when relativistic effects are unavoidable, and they've done so across cosmic time. We observe quasars from many epochs, from the early universe to the present day, watching how they evolved, how their properties changed, how their role in cosmic history shifted. This time dimension is crucial. The universe has a history. It began in a specific state, the Big Bang, and evolved according to physical laws. By observing quasars at different redshifts, we're watching different chapters of that history. We're seeing how the universe changed from its youth to its current middle age, and we can extrapolate forward, predicting what comes next. The universe will continue expanding, galaxies will become more isolated, quasars will become rarer, star formation will decline, eventually the cosmos will darken, but not yet. Not for a very long time. For now, quasars still shine, supermassive black holes still feed, jets still launch, feedback still regulates galaxies. The universe is still dynamic, still evolving, still presenting us with phenomena to observe and puzzles to solve. You've spent time now, across these two explorations, learning about quasars, from their discovery in the 1960s as mysterious radio sources, through the decades of theoretical development that explain them as accreting black holes, to the modern era where we study them in exquisite detail and use them as tools for cosmology. You've learned about the physics, accretion disks, jets, feedback, magnetic fields, relativistic effects. the complex interplay of processes that makes quasars what they are. You've learned about the observations, spectroscopy, variability studies, multi-wavelength campaigns, reverberation mapping, microlensing, gravitational wave detection. The techniques we've developed to probe objects billions of light years away. You've learned about the records, the most distant, most luminous, most massive, objects that push against the boundaries of what should be possible and force us to reconsider our models. And you've learned about cosmic history, how quasars reionized the universe, shaped the large-scale structure, regulated galaxy formation, enriched the intergalactic medium, how they're integral to the story of how the cosmos evolved from its early simplicity to its current complexity. This is real knowledge, built on decades of observation and theory, tested against data, refined through the scientific process. It's not speculation or storytelling. It's our best current understanding of how the universe works, and that understanding continues to grow. Every year brings new discoveries. Every new telescope extends our reach. Every new detection adds detail. The universe is revealing its secrets, and we're learning to read them. But knowledge comes with a kind of vertigo. The more you understand, the more you realize how much remains unknown. Every answer generates new questions. Every solved mystery reveals deeper mysteries. Why do supermassive black holes exist at all? How did the first ones form? What determines their final mass? How exactly do jets launch and collimate? What's the detailed structure of the innermost accretion disk? How does feedback couple to galaxy evolution on all scales? We have partial answers to these questions, frameworks, models, but the details are uncertain, the mechanisms are complex, the universe is not obligated to be simple. And that's okay. That's the nature of frontier science. You work at the edge of a knowledge where understanding transitions to uncertainty, where models become speculative. The quasars don't care whether we understand them. They exist according to physical law, indifferent to our theories. Our models are useful to the extent they match observations, and they're constantly being tested and refined. This is humbling. We're not the universe's masters, decoding it at will. We're explorers, tentatively mapping unknown territory, occasionally making wrong turns, gradually building a more accurate picture. But the progress is real. The understanding we have today is vastly greater than what existed 60 years ago. And 60 years from now, our descendants will know far more than we do. Science is a cumulative enterprise. Each generation builds on the work of previous ones. Newton saw further by standing on the shoulders of giants. We stand on Newton's shoulders, and those of Einstein, Hubble, Chandrasekhar, Eddington, and countless others who built the edifice of modern astrophysics. And future scientists will stand on our shoulders, using the telescopes we built, the data we collected, the models we developed, as foundations for their own discoveries. The exploration of quasars is part of this larger story. The story of humanity's attempt to understand the cosmos, to answer the fundamental questions. What is the universe? How does it work? Where did it come from? Where is it going? Quasars are one chapter in that story, an important one. They've taught us about black holes, about accretion, about relativistic jets, about feedback and galaxy evolution, about cosmology and the large-scale structure. But they're not the only chapter. There are other cosmic phenomena to explore, other mysteries to unravel. Dark matter, dark energy, the very early universe, the nature of time and space, the possibility of other universes. Each of these represents a frontier, an area where our knowledge is incomplete and new discoveries await. The universe is vast, richer than we can fully comprehend, more complex than any model captures completely, and we're only beginning to understand it. But what a beginning it's been. From ancient humans looking up at the night sky and seeing gods and myths, to modern astronomers using instruments of incredible sophistication to probe the depths of space and time. From wondering what stars are to understanding stellar physics in detail. From noticing that some stars move, differently to discovering planets, solar systems, galaxies, the expanding universe, dark matter, dark energy, black holes, quasars. Each step has expanded our perspective. Each discovery has revealed the universe to be larger, older, stranger than previously imagined. And quasars, these brilliant beacons powered by supermassive black holes, are among the most remarkable phenomena in this remarkable cosmos. They exist at the intersection of the extreme, where gravity becomes so strong that not even light escapes, where matter accelerates to near-light speed, where magnetic fields channel energy across millions of light-years, where physics operates at limits. They're beautiful in an abstract way, not aesthetically. A photograph of a quasar is just a point of light, but conceptually, the elegance of the mechanism, the efficiency of energy conversion, the feedback loops that regulate growth, the connections to cosmic history. There's a deep satisfaction in understanding, in knowing that what appears as a faint speck in a telescope is actually a supermassive black hole accreting matter, radiating with the light of trillions of suns, affecting its environment across cosmological scales. In knowing that this object's light has travelled for billions of years to reach us, carrying information about conditions in the early universe. In knowing that by analysing that light, its spectrum, its variability, its polarisation, we can reconstruct the object's properties, its black hole mass, its accretion rate, its spin, its structure. This is the power of science, the ability to look at light, photons that have crossed the cosmos, and extract knowledge, to use physics and mathematics as tools for decoding the universe's messages. Is not magic, is not mysticism. It's a systematic process of observation, hypothesis, prediction, and testing. But the results can seem almost magical in their power and reach. We can study objects billions of light years away. We can probe the universe when it was young. We can test the laws of physics under extreme conditions impossible to reproduce on Earth. And we can do this because the universe is comprehensible, because it operates according to laws, because those laws are consistent across space and time, because the same physics that applies here applies there, in the distant past, in the depths of space. This is not obvious. The universe could have been chaotic, lawless, impossible to understand, but it's not. It's structured, orderly, governed by mathematics. Why? That's a deeper question, perhaps unanswerable, but the fact remains. The universe is knowable, and we, briefly, have the capacity to know it. Rest now. You've absorbed a tremendous amount of information across these two explorations, from the discovery of quasars to the physics of accretion, from the role they play in cosmic history to the records they set, from the observations that constrain them to the future studies that will. Reveal more. Let these ideas settle into your mind. Let them reorganize your sense of scale, of time, of cosmic history. Let them inform your understanding of the universe you inhabit. You live in a cosmos where supermassive black holes exist, where they accrete matter and shine as quasars, where their influence extends across galactic and cosmological scales, where they've shaped the structure you see around you. This is your universe, a place of extremes and limits, of structure and evolution, of comprehensible physics operating across unimaginable scales, and we're learning to read it, to understand it, to place ourselves within its vast story. The quasars are still out there, shining across cosmic distances. Some are actively feeding, brilliant beacons visible across billions of light years. Others have faded, their black holes dormant, waiting patiently for the next meal that may come in millions or billions of years or never. But they persist, monuments to gravity, engines of transformation, teachers of physics, records of cosmic history. And we, for a brief moment in cosmic time, have the privilege of studying them, of understanding what they are and what they do, of using them as tools to probe the universe's structure and evolution. This is the culmination of our exploration, from mystery to mechanism, from confusion to clarity, from discovery to understanding. The quasars have revealed their secrets. Not all of them, some mysteries remain, but enough that we can say with confidence, we know what quasars are. We know how they work. We know what they've done to the universe. And that knowledge, hard-won through decades of observation and theory, is one of humanity's great achievements. Sleep well. Dream of distant lights powered by gravity's ultimate expression. Dream of matter spiraling into oblivion while radiating across the cosmos. Dream of the universe in its youth, when quasars were abundant and the cosmic web was forming. Dream of the future, when telescopes more powerful than any we have today will probe quasars in unprecedented detail, revealing new physics, testing theories, pushing the boundaries of knowledge. The quasars are waiting, patient, eternal on human timescales, ready to teach us more about the universe they helped build, and we will keep learning. This is the end of our quasar journey, from discovery through understanding to appreciation. You know what they are now. You understand their role. You've glimpsed the extremes they represent. The universe is richer for containing them, and your understanding is richer for learning about them. Until we meet again in some other exploration of deep time, some other journey through cosmic history, rest well. The universe continues its expansion. The stars continue their burning. The black holes continue their patient waiting. And somewhere, billions of light years away, a quasar shines.